So thank you all for coming. So this is the second lecture of a lecture series that we are doing. I was a bit ambitious with the topic I wanted to cover. I wanted to cover kind of consensus mechanism scaling, governance, game theory, and cryptoeconomics, and I realized that's just way too much. So I'm cut in half now, so I'll just be going through proof of work, proof of stake, delegate proof of stake, and go through some principles of governance, and then talk about one example of how we can use game theory in order to ensure that we can get to a resolution regardless of people's incentives. So I think we will start with proof of work. Okay, so in the last lecture we went into how proof of work actually works and how we do reach a sense of consensus. So we went through the technicals, went through cryptography, went through all that stuff. So I just want to go through it quickly, and then we'll talk about some of the issues maybe that we have with proof of work. We have minds in the proof of work consensus mechanisms, and they try to solve a cryptographic puzzle. And the first one that solves the cryptographic puzzle are then recognized the network to be able to have the rights to mine the next block, and then they get the opportunity to then write transactions themselves, which is the reward, which is the Bitcoin reward. As I just said, the protocol says that the first miner who achieves the correct solution gets the authority to mine the next block. The difficulty is defined by a predefined number, which is like 10 minutes. 10 minutes is needed to ensure that we don't get too many hard forks in the system, amongst other things. So the difficulty changes depending on how quickly the previous blocks were mined. So at the beginning, when Satoshi created proof of work, his idea was, well, if one person has a CPU, then they could theoretically have one vote. They can have a say in the state of truth of the system. So this worked great at the beginning, 2009, when everything was just getting started. The problem is that, yes, anyone can onboard the system, but as technology advanced and more people got on the network and more people realized how lucrative the Bitcoin network was, people started to produce FPGAs and then got into ASICs. And what happened was, it became more and more economically infeasible for someone to use a CPU to mine on the Bitcoin network and have a vote and have a say in how things work. So we had this sense of centralization where it's not just anyone. People who had a certain amount of money had to have that money before getting to the network, and it acted as a sense of centralization, which I guess Satoshi maybe even envisions aggregation of hash power. So we have the advent of pools. So basically now we have people who want to still get a block reward aggregate that hash rate power into a pool because they understand that if they understand that if they just mine out their own CPU, it might take them 50 years before they actually get a mining reward from a block. So they decide, well, let's bring all our hashing power together and then see if we can get a block in the next 2 days or 3 days or a week or so. And then once we get a reward, we will segregate the rewards dependent on the amount of hash power you contributed when the block was mined. And so now we have a centralization of computational power. And this is a real problem because through this methodology, now we have 81% of all pools who host hash rate power in China, and 71% of all the hash power comes from China as well. And why? Well, power is extremely cheap in China, and it costs about $3,000 per Bitcoin to mine it in China, and they have access to very cheap and very quality hardware. So in China, we have very large warehouses where they have a large proportion of the hash rate of the Bitcoin network is come from. So you might ask the question, well, if the Chinese government hits a point where they've said enough's enough, we want to destroy Bitcoin, they can just go along and then seize all these Chinese farms, and instead of it being every single person in their house with one CPU, now you have maybe 100 farms all across China that are easily seizable. You can't seize 10,000 people's worth of computers, it's logistically infeasible. But now that you can do that, it really creates a possibility for people to be able to take the hash rate power and potentially attack the network. We have this idea of the Great Firewall of China. So right now, China definitely filters packets of information through the internet with information coming in and out of China. And this is a bigger issue because there might be a point in time where China goes, if they can, I don't know if they can figure this or not, but if China can, they can say, look, we're not going to accept any Bitcoin packets coming into our country, so we're going to create this proverbial firewall. I've been told that apparently this is not possible because Bitcoin transactions are so small, it's indecipherable between Google transactions, but Google information packets, but I don't know if that's the truth. Rusty Russell said that, so I probably should believe that. Yeah, and so they could theoretically say, look, we're not going to accept any more Bitcoin packets in the network, and the problem with that is that it really segregates blockchains. You have one blockchain, which is the world's blockchain, which is what everyone's contributing to, and then you have a Chinese blockchain, where all the Chinese participants are mining on. The problem with this is, though, that the blockchain and the Bitcoin network says that the longest chain with the most computational power on it is the one state of truth. Now, if we have this Chinese firewall cutting the Chinese blockchain from the world's blockchain, then what's going to happen is because China has 71% or so of the hash power, the Chinese blockchain is actually going to be a lot larger than the world's blockchain because they've had more hash rate and more computational built upon it. So you can imagine that maybe the Chinese government say over the next month we're going to block the firewall, and then a month after they reopen it. Now you have a Chinese blockchain that could be manipulated by these pools and by these factories, in their number of 100 or so, create all the transactions for themselves, rewrite transactions from the past, and then that gets introduced in the world blockchain. And even then the world blockchain goes, no, we know these are frauded transactions. The Chinese blockchain has the most proof of work, and so they're required to accept it. And so that's essentially a 51% attack, and that's a real big issue. So this idea of pooling hash power and having most of the hash power in China is really centralized the network, which is, again, I guess, against the thesis of what Bitcoin is all about and the problem it solved. So another big issue about Bitcoin is that it's used a lot of computational power, like an exorbitant amount of computational power. It currently uses 73 terawatt hours of energy, and that's the equivalent of all of Austria, apparently, which is a ridiculous amount of power. A lot of the time, especially in Canada, most of the miners use hydroelectric power. So that's just, they use renewable energy, pump water up to the mountains, and then they use the water when it comes back down as power. So that's fine, but in China, most of the power derives from coal. And we have this idea that Bitcoin is revolutionary. The first time in history, we have a protocol that's in a bank, but we're kind of ruining the climate at the moment. So this is a problem that probably needs to be solved. And so this brings on the idea that possibly we could derive alternative consensus protocols where we reduce the need or remove the need for you to have computational power to secure a network. And so, okay, so beforehand I discussed why, even though the network has been centralized and it may be actually possible to hack the network, why has the network been hacked? And I'll go into that later. It's quite interesting. Yeah, so how we solve the issues with power expenditure, how we solve the issues with centralization, maybe we can postulate alternative consensus protocols. So then we're going to proof of stake. So what is proof of stake? So what if instead of using computational power, we said instead that, look, if you own 5 tokens, you get 5 votes into deciding, you get 5 votes in the system, and the system goes, look, we're going to use a random number generator, for example, and if it so comes to be that the random number generator picks you on the network, then you get right to write the block. Now, if you have, the chance of you actually being able to write a block is dependent on how many votes you have in the system. So let's say you had 1 million tokens in the system, and if you had 5 votes in the system, then you had a 5 in 1 million chance of being able to write the block. So the idea is that the more tokens you have, the more the voting power you have, and it creates some buying pressure. It creates a reason why someone would want it to own the token to get a vote in deciding what the state of the blockchain will be. Okay, so right at the beginning, when proof of stake started, I think it started with Peercoin, and it was literally a very direct proof of stake. It was like, look, if you own a token, you get to vote, and that's it. And there's a few very big issues with this. But before I get into that, the people who own the tokens and then get the ability to write a block, previously we called them miners because they provide computational power, but in this case we call them forgers because they get to forge the block. They don't mine the block, they get the chance to write it. So in this context, instead of miners, called forgers, or validators, some people call them. In this case, if the proof of stake blockchain only has a certain amount of coins, then when forgers write a block, they only get a part of all of the transaction fees. But if there's a fixed monetary supply, so for example, there's a fixed amount of inflation for the coin, they also get the transaction fees and their transaction. They get the transaction fees as well as the forger's reward. The problem is though, that what if someone has most of the tokens? What if someone has 51% of the tokens? That's literally a 51% attack, and why would you use a proof of stake mechanism like that when you can use Bitcoin? And so the problem is, how do you disincentivize people to accumulate a ton of tokens, or if they want to accumulate a ton of tokens, how much friction can you add to that process to disincentivize them from doing so? Yeah, so I've got a bit into that. And so, as this is one example of being able to attack the network and do a 51% attack, there are many other attack vectors that can be performed on proof of stake. And there are a possible amount of solutions that might solve some of these issues. So we talked before about how any number of tokens gives you the proportionate amount of votes. Well, what if you had a system where we had a thing called quadratic voting, where so look, if you have one token, you can have one vote. Or if you had 4 tokens, you only get 2 votes. Or if you had 9 tokens, 3 votes, or 40,000 tokens, you get 200 votes. The idea is that you can chuck as much cash in as possible, but the amount of voting power you get is through a power law, and so it's kind of almost like a rate of diminishing returns. You can put in an exorbitant amount of money in, but there's not really any point in doing so. And so maybe that's a way in which you can disincentivize people from accumulating a lot of tokens. There's another problem. So basically, proof of stake now in many coins uses staking, but I haven't gone into that yet. But before staking was implemented, we have this issue where you have this person who had tokens, and they said, look, we now have the right to vote on a certain blockchain, and there are multiple hard forks. Now, generally, what you'd want to do is you want to disincentivize people to verify fraudulent hard forks. But in this case, because no one has any disincentivization to validate fraudulent transactions, people decide that we're just going to put our block on every single hard fork, and whatever hard fork wins, it just means that we cover ourselves. So we always win regardless of what transactions we verify. Now this is a really big issue, and the reason why this happens is because in the Bitcoin network we have a thing called realized costs, which is Bitcoin miners have to spend money on infrastructure, they have to spend money on real estate, they have to spend money on energy, spend money on employment and all these other things in order to have the opportunity to write the block. But in proof of stake, without staking your token, we'll talk about in a moment, you have nothing to lose if you decide to put your block on a fraudulent hard fork. And so that's a real issue because you want people to be chucking their blocks on the right version of the blockchain. And so it's really hard to create consensus then if you can't disincentivize bad behavior. And this is called the nothing at stake problem. So to solve this problem, we add the staking mechanism. So you would think that when you have proof of stake, the staking mechanism would just happen from the beginning, but that's not the case because I don't know. But maybe they wanted to do that eventually, but they just didn't write the code. So that's interesting. So the idea is in proof of stake, we can mitigate maybe this issue of being unable to disincentivize bad behavior by saying like, look, if you want to have the chance of you being able to have the vote in writing a block, then you have to stake a certain amount of money. So it might be 30 ETH, which is $6 grand US. So you have to pay $6 grand US in order to be able to participate in the network. And if the network decides that you're being fraudulent, then your stake goes away. And so now we have the potential of economic loss for a miner, for a forger. And so this now incentivizes some type of good behavior because they know that if they behave bad, they'll lose their money. and they don't want to lose their money. So that kind of covers proof of stake to an extent, and staking, and how that potentially can compete with proof of work. One of the great things about proof of stake is that all you have to do is stake, which is literally a bunch of bits that tells a program to stake your coins, and that's it. You don't have to use an exorbitant amount of computational power in order to be able to participate in the network. So that's really great. Now we're saving the climate, right? Now, so proof of stake is really like a direct democracy. It's like going to everyone. There's a million people, so that everyone, you have a direct vote. You can vote on what you want to be right, and that can work. But you can imagine that in a blockchain network where every other forger or node has to send information to every other node, it takes a very long time to be able to collect all the votes together and to get consensus and be able to scale throughput. It's a real big issue. So really, we have the advantage of saving computational power. The advantage of saving energy, and maybe being able to code some game theory incentives, but throughput's really bad. You only can do 3 to 5 transactions per second, and not the Visa of 10,000 transactions per second, which is required for scaling to the real world. So maybe we can use a representative model, which is delegated proof of stake, where we can instead have people who are part of the network vote other people who then become the validators, right? So in this case, we have network participants vote witnesses. So for example, in EOS, I do believe that we have 21 witnesses. So in a normal proof of stake protocol, you can have hundreds, thousands, if not tens of thousands of network participants all petitioning to be able to have the right to vote on the blockchain. In a delegated proof of stake model, there's a specific amount of validators that get to participate in the network. And for EOS, for example, it's 21. And the reason why that's the case is in proof of stake, if you have 10,000 different forgers or validators, they all have to communicate with each other through a distributed system. But in a validator system, delegated proof of stake system, you have 21 validators. You only need to have 21 entities communicate with each other. So being able to transfer all the information and being able to reach consensus is much, much faster. So I guess this is akin to a representative democracy, which is apparently what Australia is in right now. Doesn't really feel like it, but so yeah, I mean that's great. You can speed up the decision-making process. You can speed up how we reach consensus and be able to scale throughput. The problem is that we really start risking centralization here. Because if you think about it, we have, I'll explain that, it makes sense in a moment. If you think about it, you have 21 people representing maybe tens of thousands or if not 100,000 of voters, right? Now, in that case, we could have it that, we can have 5 or 10 validators who decide after they get voted in, they want to collude with each other and they attack the network. Now we have a centralization of decision-making power. You only have to convince maybe 12 people in order to enact on an attack rather than convincing 5,000 independent people to enact on an attack. So this is, it really is a sense of centralization. Now the idea is that the voters have the right to then vote out validators if they're acting badly. Okay. The problem with that is that you need people to actually vote. In Australia, people vote because they get a fine, but in America, for example, people don't vote. They don't need to vote. Vote's voluntary. So if you have bad actors, bad validators on the network, and you have a lot of people in the system who are incentivized to break down the network, and you don't have enough voters who really want to vote in good validators to ensure the network works, then perceivably you're centralizing power and you can attack the network much better. And this is a real issue. For example, EOS, right at the beginning when it came out, they had a massive issue with voting attendance. I think only 3% or 5% of token holders actually decided to vote. And so they really needed to push a lot of people who hold tokens to actually vote before they can reach any sort of consensus. Because if you only got 5% of token holders voting, then you can't really reach consensus on anything because no one's voting on a validator to actually ensure good governance is happening. So there are a lot of issues with this as well. And what we can see a lot of the time is if a validator starts acting in a bad way or the vote demographic changes, you can get a quick swap of validators. And I made an analogy here, there's slightly quick swapping prime ministers. in Australia. So we're going through like what, 7 now? It's kind of the same thing. Not really, but kind of. So I'm just going through this topic before. Voting is extremely important, and to incentivize people to vote will be really important to delegate proof of stake. Okay, so now we go into the idea of governance. So there's a quote there. Governance refers to all actions, such as decision-making processes that are involved in creating, updating, abandoning formal and informal rules of system. Now, governance is the very center of blockchain technology. The whole point of blockchain technology is how do we reach a consensus in a decentralized system when we have no central authority, right? And you have to use the principles of governance, the principles of making decisions, creating infrastructure and structures and how people act in a certain way and how processes are informed to ensure that we can consistently have a decentralized consensus that forms one true state. And so with all the talk that we've done about proof of work and how it works, and then proof of stake and all this stuff I'm talking about, we've actually been implicitly talking about governance the entire time. Governance is a very important topic, and we have great examples of a great model of centralized governance because we've had governments and we have corporations and we have entities for thousands of years. So we have a good idea of how centralized governance works, but we don't have much of an idea of how decentralized governance works because it's quite new. There have been research in the past, but now we have an enormous amount of incentive to solve this puzzle of how to working out how to get valid decentralized consensus for governance. And if someone solves that problem, they'll probably be the next trillionaire because it's an enormous problem. And everyone across the world, the smartest minds in the world, trying to figure that out. So there are 3 main types of governance. So there's blockchain and network governance. That's the idea of how do you reach decentralized consensus, what are the different mechanisms in place in order to reach consensus. Then we have funding governance, and that's the whole idea of how do you incentivize with people to actually do work in the protocol? How do you ensure this? It's like a different way of incentivizing people to do work because I don't think you can inherently just trust on the faith of people spending their own time on building a system. And Bitcoin at the beginning started with open source protocol, but now we have 3 backed companies, Blockstream, and there's 2 others. I forget the names now. Someone can tell me. They're all VC backed and all work in the Bitcoin blockchain. So that's part of funding governance. We also have project governance as well. Like I said, we have been implicitly talking about governance models, but we've really only been talking about blockchain network governance. And for the rest of this lecture, we'll probably just focus on that because the other 2 topics go into the ideas of token economics. And I can't go through that now because it'll take way too long. And it's quite fascinating, so I don't want to cheat it out. So what is governance? What is good governance? So when you want to ensure that you have a protocol or a structure or decision-making process in order to reach and get people together to reach consensus on how things work, you have to ensure that you have effectiveness and efficiency in the governance. You have to ensure that there's actual participation and people wanting to participate in the network. You have to ensure that when something bad happens and there's laws to prohibit that or laws to enact consequences of that actually is executed. There's some transparency in the governance model, so when you have all these people contributing to the network, that you have to ensure that they are being transparent with each other and also exchanging information the right way. They're not siloing information for their own good. Accountability, so if someone acts bad, there's repercussions for that, and responsiveness. So when something happens, the network or the protocol responds quickly. But if there's no central authority, then how do you incentivize good or bad behavior? So we have the whole topic of game theory, and the whole point of game theory is how do you ensure that no matter what the incentives or people are, how do you ensure you create a mathematical model such that you always get the same resolution regardless of people's incentives? Because at the end of the day, in blockchain, the end goal is to get to a one state of truth no matter what people want to do on the network. They can be adversaries and try to attack the network, and you have people who want to participate in a good way. At the end of the day, the same resolution is met. And the whole idea is that through game theory, through building out models and playing with economic, psychological, and other incentives, you can always ensure that resolution at the end is reached. So at the beginning, I kind of went through some of the issues of proof of work and how there are issues with centralization, and you maybe even have perceived that it is actually physically possible to hack or attack the Bitcoin network. Beforehand, the whole idea of Satoshi Nakamoto's vision was that it would actually be impossible if you attack the network. No matter what you do, it's extremely hard, because how would you be able to convince thousands upon thousands of individual people who have the CPUs at home to attack the network? We now have pooling of hash rate and all that type of stuff. Now, it is actually physical to hack the network, but why hasn't that happened? Bitcoin's 9 years old now and it hasn't been hacked yet. So let's think maybe of a situation where it could possibly get hacked. So we go back to the firewall situation again, and we say, look, China has had enough. For the 10th time, they've banned blockchain, they've banned Bitcoin. They go, no, this is not happening. But for real, they actually do something about it rather than just try to create FUD in the markets, fear, uncertainty, and doubt. People don't know. Let's take a look. We're going to enact the firewall, but we're going to enact the firewall. We're going to take over the miners in China, and we're going to create our own fraudulent blockchain, and then after a month, we're going to re-merge our blockchain with the world's blockchain, and the world blockchain is going to have to then merge. The problem is that people who participate in the world blockchain are going to realize that China, or the Chinese blockchain, is fraudulent. They've changed all the transactions, and the world blockchain is going to look, we don't want to participate in this. But the biggest problem is that for the first time in history, the Bitcoin blockchain has been hacked. It's never been hacked before. And the entire scope of the industry is that Bitcoin is super secure, and it is the very premise of blockchain. Now, if Bitcoin gets hacked, it kind of means that blockchain doesn't work anymore, and you can imagine that the Bitcoin price would just die. It would just, it's dying now, but it would truly die. It would go to zero. And so you think to yourself, well, you can definitely see that would happen. So why would then someone attack the network? Because you can say that someone has 1 million Bitcoin, or through hacking or attacking the network, for example, in China, they're able to accumulate 1 million Bitcoin. That has to have value, right? But if they attack the network and now the entire market doesn't value anymore, you have 1 million Bitcoin, but they're only worth $0 or $1. And so really what you're doing is self-sabotaging yourself. So maybe Bitcoin hasn't been hacked yet or attacked yet, not because it's physically impossible, but there is no economic incentive to actually attack the network. And so this is kind of game theory. This is creating incentive or disincentivization models to ensure that at the end of the day, you still reach the resolution that you want. Now, that's a very simple economic disincentivization on the Bitcoin network. The idea is when you have these proof-of-stake tokens and you have Ethereum, where you have smart contracts. Yes.
What if that's what they want to do? Like, what if there's economic gain in not having Bitcoin working against its reputation?
Well, that could definitely be the case. Maybe that the government wants to spend 10 billion in hash power just to kill Bitcoin, but it might be also that the world's blockchain goes like, look, we recognize that you've done that, but we're going to change the code a bit, and we're going to create our own hard fork, and the whole entire world blockchain just decides to spend on a hard fork and they just ignore it. That's another thing, and maybe you could attack the network and then do that, but if you do that at the beginning as the first attack, then it would be really bad sentiment hit into the market. So that could happen, and maybe the market and the network could be super resilient and build a new blockchain and everything would be fine. But it would really hurt sentiment a lot, and I think a lot of developers would be like, yeah, it would really hit them. So that's a possibility. What was I saying? Oh yeah, you could code in smart contracts disincentivization models, so that you can create much more complex models, mathematical models, to ensure adequate behavior. So then this goes into the idea of token economics. How do you use tokens that are programmable in a certain way that people can only interface in a certain way? And because they can interface in a certain way due to the code, that creates, for example, buying pressure, or causes people to transact with that token, or a bunch of other things. So this goes into the idea of token economics, which I'm not going to go into today. It's a really big topic, and I'll go into it next time. Yeah. Yeah, so I guess the general scope is governance is everything, and everything about blockchain is governance. And if someone can solve that problem, yeah, I think the space would be doing really well. So yeah, I think that's it. Does anyone have any questions? No. Okay. Thank you.